Perfect. Okay, so let's start. Good afternoon to all the participants, and I welcome today's speaker, Dr. Amol Dighe, Tata Institute of Fundamental Research, my faculty colleagues and student friends, and the participants from other institutes. I can see there are many, to our eighth lecture under Frontiers in Physics 2020. So a series of lectures by eminent Indian scientists. So this series of lectures aims to expose the next generation scientists to the potential frontiers in physics and beyond. So with this aim, today we have Professor Amol Dighe. He is a professor of physics in Tata Institute of Fundamental Research in the Department of Theoretical Physics. He works in the area of high energy physics, which aims to understand the nature of fundamental interactions by studying properties of elementary particles. His recent research has focused on the particles known as neutrinos, their nature, and the role they play in astrophysics and cosmology. He looks for signals of new physics at experiments like the one at Large Hadron Collider CERN, and in the particles that come from the sky. So, to introduce Professor Dighe, he completed his BTech in Engineering Physics in 1992 from Indian Institute of Technology, Bombay. And then he did MS and PhD in 1997 from University of Chicago, USA, where he explored signals of charge parity violation in particle physics interactions. Later, he was a postdoctoral researcher in ICTP Trieste, International Center for Theoretical Physics, which is in Italy, CERN Geneva, and Max Planck Institute of Physics, Munich, Germany. Before, he joined as a regular faculty member in 2003. And it is highly encouraging to note that he was one of the first Indian bronze medalists in the International Mathematics Olympiad held in Germany in 1989. He has received the Institute Silver Medal from IIT Bombay and World Lab CERN John Bell Scholarship. He was the leader of the Max Planck India Partner Group in Neutrino Physics and Astrophysics for 5 years. He has been elected Fellow of the Indian Academy of Sciences and the Indian National Science Academy. And he has won the Shanti Swarup Swarnajayanti Fellowship from Department of Science and Technology, and he is a recipient of the Shanti Swarup Bhatnagar Award for Physical Sciences. So this is highly encouraging to note the achievements of Professor Dighe. And with this, I welcome Professor Dighe, and he is going to talk about neutrinos, a new window to see the universe. So, Professor Dighe, you can start now, and we'll take up the questions towards the end. So, no intervention to the speaker in between.
So, in fact, yeah. So, actually, what might be good is I have actually divided my talk into certain sections. Okay. After which I will stop. And if there are any questions, it will be nice to take them at that time. So
perfectly fine. So that the doubts are not carried over.
You are the boss, so you.
Perfect. Thank you.
Okay. Yeah. So let me just check. Is my screen fully visible now?
Yes.
Okay. So let me start. So thanks for that kind introduction, Raghunath, and also want to thank IIT Indore for inviting me for this. I think this is one advantage of being in this pandemic and working from home, is that you could actually virtually go to many places and talk to people there. I think we are getting more and more used to this. Okay, so today I'm going to tell you about neutrinos, which happen to be my favorite particles. I don't know how many of you are familiar with this, but I'm going to assume almost zero familiarity. So those of you like Shubhendu who are experts in neutrinos might find the first part perhaps too familiar. Okay? But I hope that I will tell you also something interesting, maybe towards the later part of the talk. Okay. As you see in this front slide, I'll just tell you what's coming here. So what you see here is a mountain. And you see from the sky shower of particles. These are cosmic rays which are coming to us all the time, and these cosmic rays reach the Earth in the form of various particles, mainly muons, electrons, and neutrinos. And what you see at the bottom here is a proposed laboratory that we want to build under this mountain. It's very small compared to the mountain. It just looks big in this picture, which will be called as the India-based neutrino observatory. But we'll come to that towards the end. Okay, first we want to learn about these particles, what these are, what their interesting properties are, and why we should care about them. So I have these 4 sections, and as I said, at the end of each section, I would stop and take questions so that everybody is with me and no people are not lost. So first I'll talk about neutrinos coming from the sun, because that happens to be the greatest source of neutrinos we have around. Then I'll talk about neutrinos in astrophysics, cosmology, and particle physics. Then talk about some of the mysteries that neutrinos have given us. And finally, I will talk about how we can use neutrinos as messengers from the universe to look at things from the universe, as I said, with a new eye or as a new window. So let's first start from neutrinos from the sun. So, of course, mankind has seen the sun shining for since mankind was there. However, it's worth noticing that we actually know how the sun shines, we'll have some idea, only for about 100 years out of these few hundreds of thousands of years when there have been Homo sapiens. Because we know that sun shines by nuclear fusion reactions, and we did not know of nuclear fusion till the start of 20th century. So we did not know that there was a nucleus and there's energy is produced when things undergo fusion or fission. So our knowledge of sun as a whole, even overall one, how it shines, is only about 100 years old. Okay, that's something surprising. So we actually do live in a very interesting time. What did this knowledge tell us initially? It told us that inside the sun, hydrogen nuclei undergo nuclear fusion. They, of course, also use some electrons around them. And finally, through many processes, end up giving you helium nucleus. And of course, finally, that gives you light. However, if you try to go and look at details of these interactions, you find that this interaction will not be able to conserve energy and momentum. Okay, if you look at the energy and momentum of all these particles that are being produced. Now, of course, in physics, it's a crime not to conserve energy and momentum, which could mean that something is missing in this equation. And as you could perhaps guess from this figure that I have on the top, what is missing are these 2 neutrinos, which are called an electron type. What is electron type? I will come to that very soon. Okay. So what this means is that unless there are neutrinos, this reaction that powers our sun would not happen. Okay. And therefore, it is often said that neutrinos are essential for the sun to shine. For looking at the neutrinos from the sun for the first time, Davis and Koshiba got a Nobel Prize in 2002, okay, just around the turn of this century. However, it's not just that we know neutrinos come out of the sun. Okay? We can observe them, and when we observe them, we learn some interesting features. Okay? So let's see some of these features. First feature is that the number of neutrinos that come to us is very large. So we are all perhaps sitting at homes in various places, or maybe sometimes in our offices. To each of our bodies, at this point of time, about 100 trillion neutrinos are passing every second. Clearly a very large number. However, none of us has noticed them so far, unless you are told that they are passing. Okay, so that's one point. Second interesting feature is that now I guess it is 4:30, maybe the sun is about to set, but even at night, at 4 o'clock in the morning, we would have the same number of neutrinos passing through us. Okay. Now, we know that of course at night sun shines, but sunlight doesn't reach us. But turns out that the same number of neutrinos from the sun reach us even during night. Okay. So whether it is 4 p.m. or 8 p.m. or 2 in the midnight or 2 in the afternoon, okay, about 100 trillion neutrinos will pass through us every second. And what's interesting is that they seem to come directly from the core of the sun. Now this is slightly different from the sunlight that we see. Note that the sunlight that we see actually comes from the surface of the sun and not from the core of the sun. Okay, so that's the major difference. So all of these facts are rather confusing and tell us that neutrinos are something very, very different from what light is like. Okay? Because light and neutrinos come from the same sun, but they seem to have very different properties. Okay? So let's try to find out what are the reasons for these confusing facts. Okay? And for that, let's go about a few hundred years ago, and maybe you are able to recognize these two individuals. It's hard to get a response on Google Meet, so let me just tell you that this is Prithviraj Kapoor and Raj Kapoor, well, also known as Akbar and Birbal. And there is this Birbal story that you may have heard of. Okay? So the story said that there was this wise man who came to Akbar's Darbar and said, okay, I'm going to ask you 3 questions and you have to give me only one answer. Okay? And he asked these 3 questions. He asked, why did the roti burn? Why did the betel leaves rot? And why could the horse not run? Okay, I don't know how many of you have heard the story before, but let me give away the punchline. The punchline, of course, after going through all this rigmarole of everybody trying to give one answer and failing, Birbal, of course, as usual, gives the correct answer. And Birbal says that the answer is that they were not moved. So, roti, when you try to cook the roti, if you don't turn the roti upside down every few seconds, it's going to burn. The pan wala has these pan leaves which he keeps on moving up and down. If not, they will rot. And if horse is not moved or just kept tied in the stable, of course, the horse is not going to be able to move. The story has absolutely nothing to do with physics, okay, except that it illustrates that sometimes 3 questions which are completely independent or look completely independent happen to have the same answer. Okay. And as all of you know, in science, if we have one answer which answers more than one question and solves more than one puzzle, that actually is the most interesting answer. So that is the answer that was being looked for by many people, among them these 2 guys. So this is, of course, Pauli and Dirac, 2 of the most brilliant and celebrated physicists of the last century. And they actually, their work focuses on these 3 problems that you see here, which are the 3 problems that we noticed. Why is it that we don't notice neutrinos passing through us? Why is it that neutrinos from the sun reach us during night? And why is it that we can see inside the sun with neutrinos? We can look at the core of the sun and not just the surface. And the answer that their work has provided is that the reason is the neutrinos interact extremely weakly. Now I want to say something about what is this extremely weakly thing, because well, it is weakly and very weakly and highly weakly and extremely weakly and so on. Let me give you one example. Okay? It's possible that some of you have done some experiments with radioactive source inside your lab, and you would have noticed that these radiation sources, usually they're alpha, beta, or gamma sources, and they are shielded by using lead shielding, okay, or iron shielding. You perhaps have some bricks that you keep around them so that you are not exposed to them directly. The thickness of this lead that you need, iron that you need, is maybe about a few 10 centimeters, maybe 50 centimeters, let's say. So 50 centimeter thick lead can actually stop these particles, because these particles interact with lead, okay, and lead therefore stops them. Now imagine that you do not like these 100 trillion neutrinos passing through your body every second, and you would like to actually build a wall between the sun and you so that no neutrino reaches you. So it turns out that even if you want to reduce this number by a factor of 2, by just make them half, you will need a few light years of light. Okay? Of course, you perhaps have realized that this is kind of absurd, because the distance between the sun and us is about 8 light minutes or so. Okay, so of course this is a completely impossible thing, which actually tells us that it is almost impossible to stop neutrinos coming from any major source. Okay, and that's what is meant by they'll be extremely weak. Okay, so you can see this difference between 50 centimeters of lead to light years of lead. Okay, so that's the difference between the weakness of let's say light, of gamma radiation, and the weakness of neutrons. This weakness actually answers all our three questions. Okay, so let's see how. So first question was, why don't we notice neutrinos passing through us? And the answer is simply that they pass through us and don't interact. So that's just it. So we don't notice them. The second question was, why is it that neutrinos from the sun reach us also during night when we can't see the light? And the reason is that because these neutrinos interact so weakly, Earth cannot stop them. Okay, so at night we cannot see the sun simply because Earth stops sunlight from reaching us, whereas Earth cannot stop neutrinos. So therefore, even at night, we can look at the neutrinos and see that they are coming from the sun, which is somewhere at the bottom, somewhere through the Earth. And the same thing tells us why we can see inside the sun with neutrinos, and that answer is that the neutrinos can pass through the sun also without interacting. So the same answer has allowed us to answer all the three questions that we had. Okay. On the other hand, this answer now begs a new question. If nothing can stop them, nothing can interact with them, how can we see neutrinos? Okay. So this is one example of how we can see neutrinos. This is not the only way, but this is the principle. So what is the principle? What I am showing you on this left-hand side is an experiment called as Super Kamiokande. It's an experiment that is in Japan. This is literally water. It's almost the purest water that you can find ever. This is a boat. This boat has three men. Okay, so they have got three men in the boat. What they are doing is they are trying to clean up these photomultiplier tubes. These photomultiplier tubes, I don't know if you can see me fully on the screen, are basically of this size. Okay, so I don't know if you can see this size, not this, but double of this. Okay, so you can see that. These people are cleaning them. This detector has 50 million liters of water. Okay, it's also called 50 kilotons. After they clean one round of these photomultiplier tubes, the water level will be raised. They will clean the next level, and so on and so forth till they come out. Okay, so it's a really, really large detector. So once you have the detector, you wait. Okay, you wait till one of the neutrinos interacts with either a nucleus or an electron and gives out a charged particle like an electron. Now, if neutrino that's coming in has a high energy, electron that's going out will have a high energy. Okay? So high that its speed will be more than the speed of light inside water. Okay? Speed of light in water is about 2 times 10 power 8 meters per second, and particles can travel faster than that. When that happens, you perhaps have heard that there is something called a Cherenkov radiation that comes out. This Cherenkov radiation is actually detected by these photomultiplier tubes. Okay? They are called so because they absorb photons and give out electrical pulses. Okay? So, looks quite straightforward. A neutrino will come, give out an electron. You look at the electron and you know that a neutrino has come. Okay? However, we know that neutrinos don't interact much. So, the observation is very, very rare. So, in one day, through this detector called Super Kamiokande FASc, about 10 to the power 25 neutrinos pass through it. However, only about 5 to 10 out of them interact in the detector. Okay. All the rest simply pass through it without interacting. Okay. So efficiency of the detector is extremely, extremely small. So if you do want to become a neutrino physicist, okay, you have to build very, very large detectors, and you have to wait for a very long time. Okay. So patience and a long life are things that are required for being somebody who works with neutrinos. Okay. So let me take a small halt here and see if there are any questions. If not, I will go ahead.
So, hello.
Yes.
Sir, as you say that we have the concept of neutrino as a particle from the conservation of momentum. So, when we the first observe the neutrino in a lab,
I will come to that very soon. Yeah? So I will talk about discoveries of neutrinos. Yeah? Thanks for the question. Okay. So I don't see any other questions. So I will go ahead and tell you about interesting facts about neutrinos in various domains. Okay. So I guess you can see this. This is a view from the Hubble telescope. These are mainly stars, galaxies, quasars, and so on and so forth. If neutrinos were not there, they would have affected our cosmology by quite a bit. In fact, without a neutrinos, there's a famous picture that tells you how the world would have looked without neutrinos, and that world would look something like this. Okay? And perhaps you can see what I'm showing here, and it's a completely black square, and that is simply because there would be nothing there to see. Okay? The result is that neutrinos seem to be the only way that we understand right now which can create the asymmetry between matter and antimatter, okay? Which means that the number of protons is more than number of antiprotons, or number of electrons is more than number of positrons. Now in the world, we actually see this asymmetry to such a large extent that everything that we see around is made up of matter. Okay? And that is because matter and antimatter have come together and annihilated completely, and a small amount of matter was left over, which is what has formed atoms and then stars and planets and galaxies. So if there was no asymmetry between matter and antimatter, all of the matter would have annihilated with all the antimatter, and you would not see any of the even atoms, forget even stars and planets. We don't know the final solution to how this asymmetry was formed, but from the current theories that we have, the only candidate that can help in this is actually neutrinos. We know that it cannot be formed simply by interactions of protons, electrons, or neutrons. Okay? So therefore, just to make this world possible, even atoms possible, neutrinos very essential. Even once that is done, we realize that neutrinos had a big role in creating the Earth. So what does this mean? So let me explain what happens. So of course on Earth, we see a lot of elements, starting from, we see hydrogen, helium, of course, but we also see carbon, oxygen, iron, aluminium, maybe gold, silver, uranium, and so on and so forth. Now, all these elements are created inside stars. And in fact, if you want to create elements heavier than oxygen, you have to have really, really massive stars. Okay, Sun can create oxygen, but to a very, very small extent. So to create these elements, there have to exist very massive stars, and not just that. Just forming elements inside does not help. These stars also have to explode so that they release the elements in space. Okay, and then finally these elements will form our solar system. So therefore, we conclude that something like a supernova must have exploded maybe billions of years ago, whose fragments form the solar system. So this tells you that explosion of supernova is essential for the formation of our solar system. And as we will learn later, supernova explode because neutrinos push the shock wave from inside and help the explosion. Okay, so I will talk about that for some time in a short while. So we already see neutrinos essential for forming, having some matter. Neutrinos essential for actually even making the Earth. Third interesting fact is that they are the second most abundant particles in the universe. Okay? So the most abundant, of course, is light, and we see that in the form of what is called as cosmic microwave background radiation, or CMB radiation, all around us. You might have heard about this. It has temperature of about 3 Kelvin, and it is there everywhere in the world. Okay, almost uniform temperature. This means that if you go to any space, no, even between galaxies, you will find about 400 photons per centimeter cube, even if there is nothing else around. Okay, so photons, these photons called as the Big Bang photons, are the most abundant particles in the universe. But very, very close on their heels actually come cosmic neutrino background radiation, which is about 300 neutrinos per centimeter cube with temperature of the order of 2 Kelvin. Okay, so almost the same temperature, slightly less, but number also is almost the same, almost 300. Okay, so photons and neutrinos, the number in the universe is way, way more than number of protons and electrons. So even empty space between galaxies is full of these neutrinos, and therefore they are extremely, extremely abundant. So these are the kind of neutrino sources that you might observe. Sun we did talk about. We talked about supernovae, but I also tell you about them sometime later. We did talk about this cosmic Big Bang neutrinos, which are about 300 per centimeter cubed. We have not seen them yet. We only have indirect evidence. Neutrinos also come from astrophysical processes like gamma ray bursts or apogalactic nuclei. And although this said soon, I will show you later that we might have seen some of them at our detectors, maybe in the last 3-4 years. I mentioned to you that these are cosmic rays that come from the sky, and they produce neutrinos in the atmosphere of the Earth, and these are called atmospheric neutrinos. And just to let you know that the first observation of atmospheric neutrinos was actually done in India. It was in Karnataka, in a mine called as Kolar Gold Field. So there was an experiment by TIFR, a Japanese collaboration, Durham University and a few, but the detectors were made in TIFR and were kept inside this Kolar Gold Field. You also get neutrinos naturally from the radioactivity of the Earth, because inside Earth crust we have radioactive elements, uranium, thorium, potassium, and so on, and they give us natural radioactivity. Okay. I don't know if you eat bananas, but banana is one of the radioactive fruits because it has potassium 40, which is radioactive in the sense that it decays by giving out neutrinos. And if you eat banana, then you yourself become a source of neutrinos. Okay, it's not dangerous at all because they just pass through without doing anything. But no, if your picture is taken in neutrinos, you will perhaps shine if you have eaten banana recently. I'm joking, of course. Yeah. So these sources are a natural radioactivity, natural sources of neutrinos. But of course, whenever there are nuclear reactors, you produce neutrinos artificially. And whenever there are particle accelerators like Sun, you also produce lots of neutrinos. So neutrinos are therefore ubiquitous. You see them all around the place. So it's good to become familiar with them. Okay? So there are 3 kinds of neutrinos, because we'll come to these kinds quite a bit in the remaining part of the talk. So I would like to just mention them. So one is called electron neutrino. Electron neutrino is that neutrino which, when interacts with something, gives out electron. Okay, that's a straightforward definition. There is a muon neutrino, and the definition is that it is that neutrino which gives you muon when it interacts with maybe some nucleus. Okay? Muon, for those of you who do not know, is exactly like electron, except that it is about 200 times heavier. Okay? And then there is third kind called as tau neutrino. This tau neutrino, when it interacts with the nucleus, will give you a tau particle, which is again similar to electron, but it is about 3,500 times heavier. Okay? So depending on what charge particle comes out after neutrino interactions, you call the electrons, you call the neutrinos as either electron neutrino or muon neutrino or tau neutrino. Sometimes a positive particle comes out, E plus, mu plus, or tau plus. So a positron, a positive muon, or if that happens, then particle as antineutrino. Okay, so these also exist, and they are called as electron antineutrino, muon antineutrino, and tau antineutrino, or sometimes they are called as mu e bar, mu bar, and mu tau bar. Okay. this is just a language that people become familiar. Okay. So neutrinos now are nicely fit inside the standard model of particle physics. So you can see these 6 quarks, they're called up, down, charm, strange, top, bottom, out of which up and down quarks are the ones that form protons and neutrons, as you perhaps already know. Other ones are unstable, so they do not form stable elements. Okay, but U and D are of course all around us. Then electron, muon, and tau, and then the 3 neutrinos we got introduced to just some time back. They are called as leptons combined together. They interact by various forces. G is the gluon, which mediates strong nuclear force. W and Z mediate weak nuclear forces. Gamma is photon for electromagnetism, and of course this Higgs boson. Okay. So neutrinos are 3 in number, as you see here: mu e, mu mu, mu tau. They are charges. They are spin half. So if you know of spin, just like electrons are spin half, neutrinos are spin half. They are almost massless, which means that the mass is at least 1,000,000 times lighter than electron, so very, very light. And they undergo only weak interactions, which means no interactions with photons, so no light, nothing with gluons. Only interaction is with Z, W, and possibly Higgs. Okay. What we have done so far is become familiar with what neutrinos are and the language that we are going to talk about. Okay. So maybe another time to have a small break and take any questions.
So there are many questions in the chat box. Maybe.
Okay, I can see the chat box. Okay, let me just see. How do neutrinos have a role in the matter-antimatter asymmetry? Can you elaborate? Okay. So it is possible, although it is not confirmed, that interactions of neutrinos and antineutrinos are different. Okay? We expect them to be different. However, of course, we also know that this is true for quarks. It turns out that with quarks, because they also have strong interactions, it is impossible to get the observed amount of asymmetry in matter-antimatter that is observed in our world. Okay. There are scenarios which are called as leptogenesis, which first produce asymmetry in neutrinos and then transfer them to forming in baryons, called baryogenesis. Okay. So this is going to take a new lecture of its own, so we can discuss about that maybe sometime later. How are we able to tell that there is asymmetry in the matter and antimatter? The way to tell that is look at the sky. Okay, and you look at the sky and you find that everything that comes from the sky, so for example cosmic rays that come to us from all around the universe, are mainly protons and not antiprotons. Okay, so we do not see antiprotons coming from anywhere, we see only protons. Okay. Second thing we observe is that remember, if there is matter and antimatter, usually what happens is if they come closer, they come together and collide and give out lots of light. Okay, so if there was antimatter hanging around in the sky, you would observe some kind of gamma rays coming out of various parts of the sky, but you would observe it. So various of these processes tell you that there is asymmetry in matter and antimatter. Okay. Will neutrinos participate in pair production? I don't know this question, but answer perhaps is yes. In the sense, neutrinos are pair produced, and neutrinos can pair produce. So indeed, yes. So they, of course, they do pair production, but not light. If you're thinking about a neutrino and antineutrino giving you photon, that won't happen because neutrinos don't interact with photon. Okay. Okay. Are there any attempts to study C and B? If yes, how they are trying to do it? I will complete at the end of this talk. We'll take up this question again. If I forget, remind me. Yeah. Okay, one question is, they are very far away. By they,
Sir,
go ahead.
you said that we observe only matter and not much of antimatter.
Yes.
So, but then antimatter can be a lot very far away, right? Like we're not able to right now see them, but maybe later on in the future we might be able to see them.
Yeah. So if there was antimatter, so antimatters have very clear signature. Okay. because let's say there are positrons hanging around somewhere far. Of course, there is some fraction, but not large. Then they would combine with matter and give you photons. So for example, electrons and positrons annihilate, and they give you photons of a very particular energy. Okay, actually it's 511 keV. There are telescopes looking around the sky which look for gamma rays of these particular energies, for example, and they are not observed. So all of these observations combined tell us that all the galaxies that we are observing right now are all galaxies made up of matter and not antimatter. Because all said and done, the universe is actually connected. No? It's not that there are blank spaces in between. We get cosmic rays that come to us from many megaparsecs. So we know that in such large distances, the cosmic rays that we get mainly have protons and not antiprotons. So that tells us that matter actually dominates.
Okay, sir.
Okay, so should we go ahead?
Hello. So,
Yeah.
I have a small question.
Sure.
Sir, why is the matter and antimatter created by anything? Means why energy change into matter and antimatter, and then again annihilate in
Because
energy again photon.
we know that energy and matter is identical. We know it from relativity. Energy can be converted to mass, and mass can be converted to energy. Okay, it is if two energetic particles, if they come together, they will tend to annihilate and make photons. That is the easiest thing for that.
So mainly we say that entropy guides the any physical process. So
Yes,
did the energy, changing energy into matter increase the entropy of this universe?
you are correct. Yeah. So, for example, take electron, positron, annihilating into two photons. Okay, and the entropy of this, the final thing, is going to be more than entropy of each electron. It exists on an average. Therefore, you would expect that all the matter antimatter would convert to photons, unless antimatter gets exhausted, which is what we expect has happened. Okay, so antimatter got exhausted by all these interactions, and we are left only with matter. See, all this thing happened long ago when everything was in a very big soup. So everything was interacting with everything else. And that's the reason that everything got to, all the antimatter particles got to annihilate with all the matter particles. And left over is what we see.
Okay, sir. Thank you, sir.
Okay. So now we'll come to these mysteries that neutrinos have taught us over the years. And one of the mysteries, of course, actually started with their existence, or the possibility of their existence, or the postulation of their existence. This story perhaps you have heard many times. Started with the beta decay. It's called as the beta decay mystery. So beta decay is, of course, nucleus, let's say X, decays to nucleus Y and electron. You can measure energy of nucleus X, measure energy of nucleus Y, and therefore you can measure energy of, also measure energy of electron. And in principle, since these two are very heavy, they will be almost stationary, and you can use your equations that conserve energy and momentum, which finally will tell you that these electrons have fixed energy. So which is determined only by the mass of X and the mass of Y. So if you wanted to plot a plot of electron energy on the x-axis and number of electrons on the y-axis, you would get something that looks like a delta function. Okay? So only energy that electrons will have is this energy, which you see near this endpoint. However, experiments were done on beta decay for many years, and in fact, you end up seeing this kind of a curve, which means the energy of electrons is quite spread over across almost from 0 all the way to the maximum possible value. And this means that energy momentum conservation is again grave danger, because if the electron energy is somewhere in the middle of the curve, half the energy of this decay has vanished. This did worry physicists quite a bit. In fact, some people like Niels Bohr even said that maybe energy conservation does not hold at atomic scales. So that was really a time of confusion, and that was the time when one of the physicists we just saw some time back, Wolfgang Pauli, made this postulate that maybe in this process there is a fourth particle which carries the remaining amount of energy. However, this particle interacts very weakly and therefore cannot be seen in the error detector. Okay? Now, those were the times when people used to feel very guilty while postulating things that you don't observe. Okay, I think theorists like me these days are sort of more shameless in that regard. We have many postulated particles, but Pauli was literally ashamed that he had to postulate a new particle which cannot be observed. So there's a letter written by Pauli to conference organizers during that time, which is, you also find it on the internet. It basically says that he has to go to his village for attending to some kind of dance. So he just wants to present his paper and read it out so that somebody else can read it out on his behalf. But he did not want to read it out, so he just gave a letter. Of course, turned out that he finally was correct, and neutrino actually was there. However, this is 1932, and nobody really believes Pauli at that point of time. Okay, because of this principle of physics, which is unless something is actually seen, you don't assume that it exists. Okay, you don't claim that you discovered it. So 1930 or 1930, I think, was the time when Pauli postulated this neutrino. Is not called as the time when neutrinos were discovered. It was just its postulation. Okay, just postulating a particle does not mean discovering it. Discovery came later. It came actually in 1956. Okay, and that perhaps answers one of the questions that came later. It was discovered by Reines and Cohen, who later on also got Nobel Prize for this. But what did they do? So what was the clever thing that they did? Now, of course, people were not silent till 1956. People were trying to actually look at neutrinos from 30 to 56 for almost 25 years. Their detectors kept on becoming better and better and bigger and bigger. So what approach did Reines and Cohen take? They said, okay, neutrinos come out from nuclear reactions. So we shall go to a place which has lots of nuclear reactions, which is nuclear reactors. Okay, so remember, the Second World War has passed. People know of nuclear energy. People have built nuclear reactors. So this actually played a very crucial part. But nuclear reactors give out some particles, okay, which they said maybe neutrinos. They didn't know what they were. However, they said, okay, if these maybe we make them interact with proton, then they might give you, let's say, positrons. Okay? Or it may happen other way around. They may interact with neutron and give you electrons. But protons are very easy, because if you take water is H2O. So more than half of water molecules are H hydrogen atoms, and hydrogen nuclei are nothing but protons. Okay, so that was quite nice. So if you have water, then protons are available very easily. Okay. So now you say, assume that something interacts with proton and gives you neutron and a positron. Okay. So this is what you would get if you try to look at conservation of various numbers, baryon number and so on. Now, you of course will get a neutron, but there are neutrons in water, so that's not a big deal. You can get a positron, but how to identify the positron? So it turns out that positron will interact with electron, which are of course also present in water, and they will give you two photons. This is the annihilation reaction, and both the photons will have energy of the order of 0.5 MeV, okay, which is equal to the mass of electron in mega electron. So if a reaction happens, you will see two photons of energy 0.5 MeV. Okay, so that's signal number one. At the same time, this neutron is now in the solution. So what you do in addition is you put in cadmium, because cadmium happens to be a very good neutron absorber. After absorbing a neutron, cadmium goes to an excited state, okay, and then decays by giving another photon. Okay. Photon also is energy is quite well known, but this comes just after a few microseconds. So if you see three such photons, two of them have this energy, 3rd has some fixed energy which I forget at the moment, but the time difference between them is a few microseconds. Then you can be sure that these 3 photons indicate that a neutrino came and did something. Okay, it's very unlikely that there will be some strange background which will give you these 3 photons. So that was the idea that they came up with, and in 1956, they actually discovered this. It was called a $1 million particle because this experiment got a funding of about $1 million, and of course later on they got Nobel Prize, so that sort of also compensated for that. Okay, so this was the discovery of electron neutrino. But people had no reason to suspect that there will be other kinds of neutrinos, because the problem of beta decay is solved. Beta decay only has electrons, so people are quite happy. On the other hand, you go ahead and see, okay, wonderful. Now, any reaction that I see which does not conserve energy and momentum should have a neutrino. And this idea was picked up by 3 other guys who decided to look at this interaction, which is a pion going to muon and neutrino. Now, people had seen, they knew how to make pions in the laboratory. So, in fact, in this Brookhaven laboratory, they had a proton beam that hit a target, and such interactions normally cause production of lots of pions. So, they had these pions and they made the detector. The detector was called as the spark chamber, so that when charged particles pass through it, they leave a track. And around this, to prevent any other background, any other rays from coming in, these pions from entering this, they use a steel shield. And again, the Second World War came handy because they used the steel shield from a nuclear submarine from Second World War, which had now had to be dismantled. Okay, what did you expect? They expected that something similar will happen. Okay, just like this, neutrino will come, interact with protons, because of course there are lots of protons in the spark chamber, give a neutron and give out a positron. Okay, so they expected to observe lots of positrons. Okay, that's the reaction that they expected. What they found was that they did not observe a single reaction with positron. However, they always observed a muon coming here, a mu plus. So then it told us that what they observed was something different from the neutrino that came out of a beta decay. So neutrino coming out of a nuclear reaction like this in accelerator from a pion were different in kind from the neutrinos that came out from. So therefore they discovered that this must be a new neutrino. So not electron neutrino, but a muon neutrino. This is the time when, so antineutrino simply because we see positive particles, E plus or A plus. So these gentlemen also got Nobel Prize in 1988 for the discovery of this muon neutrino. So both the discoveries of electron neutrino and muon neutrino actually were quite serendipitous. Well, I won't say serendipitous, they were quite important and unexpected. Tau neutrino was discovered actually quite recently in about 2000, and by that time we knew the standard model well, so that was not a big deal, so I will not go to that. But over these 40 years between 1960s and 2002, people were also faced with another mystery, actually 2 main mysteries. One was called as the solar neutrino mystery, and one was called as the atmospheric neutrino mystery. Now the solar mystery was the following. So, see, we know how much energy the sun gives you. So we should know how many electron neutrinos the sun gives you. Okay, and once that is done, we should know how much we should observe. Okay, the calculation is straightforward, but turns out that only half of the expected electron neutrinos were observed on Earth. Okay? So this mystery lasted for almost 40 years. A similar mystery happened with the neutrinos in the atmosphere, because it turned out that number of, if you look at neutrinos coming from the cosmic rays, Number of electron neutrinos were almost exactly what we expected. But number of muon neutrinos reduced by half if they go through the Earth. But we knew that Earth is transparent to neutrinos. Earth does not stop neutrinos. Okay? So something else must have happened. So these two mysteries were the ones that really puzzled the physicists for a very, very long time. The third mystery, which actually the measurement came in 2012, so just about 8 years ago, is that when you try to look at number of neutrinos coming from the reactors, we found that about 10% of them are actually lost. So, of course, by this time, the solution was known, so you were not very surprised. But the first two actually surprised people a lot. The solution to this, which I will just give away because we will not have much time to discuss how it came about, that's another talk. The solution to this is that these electron neutrinos perhaps would have converted to muon neutrinos or tau neutrinos. Okay. Similarly, the solution to the atmospheric neutrino mystery would have been solved if the muon neutrinos changed to tau neutrinos. Okay, not to electron neutrino because no electron neutrinos did not change in number. Similarly, the reactor neutrino anomaly will be solved if the electron neutrinos or antineutrinos that came from reactor have somehow changed to other flavors, muons or tau. For actually confirming this, there were two more Nobel Prizes, and these were, of course, more recent in 2015. So perhaps you might even have remembered that these Nobel Prizes. So we again come back to the theme of our talk, which is three questions, which a priori could be unrelated. So I don't show you the picture of particular physicists now, because neutrino physics now is not an endeavor done by a single person. It's actually done in quite big groups. Okay, so these are people in the neutrino conference, maybe about a few hundred in number, which would participate in solving these puzzles. So we have three puzzles. Why did the electron neutrino from the sun change into other kinds? Why did some of the muon neutrinos became tau neutrinos? And why did some of the neutrinos from the reactors became mu or tau neutrinos? And turns out that the answer was 1, and that answer happened to be because neutrinos have different masses and they mix. Once you have this, then quantum mechanics takes care of the rest. You give this about these initial conditions and give that to somebody who can do quantum mechanics problems. I'm sure all of you can do them, and the neutrino oscillation comes out to be in a very, very straightforward way. Okay. However, this tells something very important, and that's very often underappreciated. So what this means is that neutrino flavors do not have fixed masses. So if you give me electron neutrino, okay, so if I give you 10,000 electron neutrinos and ask you to measure their masses by whatever means you can, okay, you will come to me saying that some 40% of them have a mass of 3 in some units, 30% have a mass of 5, and 30% have a mass of 15. Actually, it ends up that any flavor of neutrino ends up giving you 3 different answers. Okay, not any 3 answers, but 3 very, very specific answers, which means that one flavor does not have one fixed mass. Okay, one flavor can have 3 different masses. Now, how can this happen? Okay, let me give you an example by using 2 flavors, because 3 flavors becomes slightly complicated. So, the flavor of electron neutrino and the flavor of muon neutrino are not the eigenstates of the Hamiltonian. I guess most of you are physics students, so you may be able to understand this language. Eigenstates of Hamiltonian or eigenvectors of Hamiltonian are states called as mu1 and mu2, which have fixed masses. Okay. So the 2 states which are fixed masses are called mu1 and mu2, but each of them consists partly of electron flavor and partly of muon flavor. And that's what is called as mu E and mu mixing. Okay. So only them have fixed masses. As a result, if you produce electron neutrino, you actually are producing both nu1 and nu2 to some extent, and then it's possible that after some time it may convert to nu. That solves the puzzle of why is it that the neutrinos can convert from one type to another. You will observe that this is of course quantum mechanics, but this is now happening for things like solar neutrinos. It's happening to atmospheric neutrinos. So it's not an experiment that you're doing in a lab with very, looking at atoms or nuclei. This is a quantum mechanics process that is taking place at very large length scale of the order of 10 to 13 centimeters for solar neutrinos. So neutrinos actually disprove the guess that quantum mechanics happens only at small scales. It also happens at very large scales. Okay, so we still have open mysteries about neutrino masses. Okay. I showed you what happens with two neutrino mixings, but actually neutrinos mix in three. There are three flavors, and these three are the three masses. Our measurements have told us that the masses, either they have one gap is small and one gap is large. However, we do not know which gap is large and which gap is small. Okay, so we don't know which gap is whether the neutrinos are arranged like the left-hand figure or the right-hand figure. Okay, left-hand figure is called as normal ordering, right-hand is called inverted ordering, and we do not know which of these is true. So we have lots of open questions that we don't know about. So we do not know if this ordering is normal or inverted. We do not know where this zero is. Okay, it turns out that our measurements right now cannot tell us what is the mass of neutrinos. It only can tell you what is the difference in the mass squares of neutrino values. Okay, it just happens because of quantum mechanics. We do not know if there are more than 3 neutrinos. There could be, but we haven't found them yet. I told you that there is this question is important for matter antimatter asymmetry. Do the neutrinos behave differently than antineutrinos? That's something very unknown. On the other hand, it's also possible that neutrinos are their own antiparticles. See, electron can't be its own antiparticle because one is positively charged and negatively charged, but neutrinos are neutral. Okay, so in principle, it is possible for them to be their own antiparticles. There are experiments which can try to determine this, but we just do not know the answer yet. And one major question that we do not know is how do neutrinos get their mass. So these are the puzzles that have been worrying us for a very long time. What we know is that neutrinos obey quantum mechanics. They form a very good, they fill in the standard model very well, and they of course obey relativity. At some point of time, in maybe again about 7-8 years ago, there was a claim that neutrinos were observed to travel faster than light, and there was a lot of excitement. However, it was soon found out that it was an experimental error, and neutrinos do not travel faster than light. Okay. So this is my third halt, and again I will take questions about neutrinos and their physics before we go to neutrinos as messengers for the. Okay. Let me keep this in front of you in case you have something. Yes.
Hello. So,
Yeah.
sir, are these eigenstate masses are fixed or not?
They are fixed, yes. It's just that we have not been able to measure them yet. We have been able to, so if the masses are, let me just specify what exactly is happening. If the masses are M1, M2, and M3, what our experiments have been able to do, they have been able to measure the value of M1 square minus M2 square. They have been able to measure the value of M2 square minus M3 square, actually just the magnitude of that. They have not been able to measure individually what is the value of M1 or M2 or M3. We only know the differences in mass squares. Yeah.
So, sir, can we predict the ratio of individual masses that give this M1, M2, and M3?
No, we cannot. See, how to determine neutrino masses, or in fact how neutrinos get their mass, is still an unsolved problem. Okay, so we do not know how neutrinos get their mass. We have a sort of clear idea how quarks get their mass, how electrons get their mass, because the interaction of those particles with Higgs boson are very clear. interactions of neutrinos with Higgs are not very clear. Okay, we do not know how much they can be. So therefore, we cannot find out ratios of these three masses. There are experiments that are being done to measure these masses individually, but they have not reached the precision needed to actually measure these masses.
Okay, thank you, sir.
I see one more question here, which I'll answer quickly. Why does the third photon get delayed? So remember, there were two steps involved before the third photon came. The neutron started moving in the liquid or water. It got absorbed by the cadmium nucleus. The cadmium nucleus went to cadmium star, or excited state. It stayed in the excited state for a small time, a few microseconds, and then it de-excited and gave you a photon. So all this delay combined was the delay that we found for the third photon. For the third photon of mass. Okay.
So,
Yeah.
hello. So, how we find the third neutrino? You have not
Sorry?
discussed that. So, you not discussed the how we find the tau neutrino.
Yeah. So I did not discuss that. So this was found in CERN in an experiment called as donut. Technology used for that was, I think, nuclear emulsion. Perhaps I will talk about it in some later talk, or just go and find about donut experiments. Okay, but this was a very well planned experiment. People knew that tau neutrino has to exist because it was needed to fit the standard model perfectly. A detector was made specially to look at decays of tau neutrino because we knew how it would decay. So we knew its decay products exactly, and the experiment was made to do that. So unfortunately or fortunately, it did not get a big publicity because it was known. But still remember that it happens to be the last standard model particle, last standard model fermion measured before Higgs. Okay. So even the top quark was not the last particle or last fermion which was discovered. It was the tau neutrino that happened in about 2000 years. Okay, so I will go to the next part of my talk.
Sir,
Yeah.
Sir, all the neutrinos that we observe in the experiment, each of them is a combination of all the three neutrinos in a different ratio.
Correct.
So is that the case only with neutrinos, or are there other particles which are in same form?
So the reason that you see it for neutrinos is because the neutrinos, when they interact only as electron neutrino or muon neutrino or tau neutrino. Okay. However, these three particles do not have fixed masses or fixed energy. Okay, the energy uncertainty is just enough that they are able to have any of the three masses that I mentioned, M1, M2, and M3. This phenomenon actually happens also for quarks. The reason we do not see it mentioned so often, one of the reasons is that it's very difficult to have quarks in an unbound state. Quarks always come as part of hadrons, and therefore it's difficult to see this phenomenon as clearly in quarks. However, if you look at, if you go and study the quarks, physics of hadrons and baryons, you will notice that there is something called as quark mixing. In fact, in 2008 or 9, I'm not sure, Professor Kobayashi and Masukawa got a Nobel Prize for their postulation that quarks actually mix. This is called as the quark mixing or CKM mixing. So the process of mass eigenstates not being same as flavor eigenstates happens in both quarks and leptons. It so happens that in the case of neutrinos, it is easier to observe because they are very small masses and they are sufficiently close to each other that when you produce something, let's say electron neutrino produced in the sun, it is very difficult to say whether it is in a mass eigenstate, nu1, nu2, or nu3.
Okay, sir. Thank you, sir.
So let me go to my next part, and of course, feel free to stop me. This for the organizers, okay? I realize that I'm sort of nearing to the time.
It's absolutely fine. This is like a we talk, so we can go ahead. No problem.
Okay, fine, sure. So now that we learned a lot about neutrinos, the question is how can we use neutrinos to find out something about the world? Neutrinos happen to be very good messengers because of two reasons. Okay? One reason is that they don't bend in magnetic field because they have no charge, which means that if you look at neutrinos coming from the sky, they point directly back to their source. So remember, we get lots of cosmic rays, but they are protons. Protons are charged particles, so they bend in the galactic magnetic field. As a result, when you see a photon coming from outer space, you are never sure where it originated. You cannot say this photon came from, proton, sorry. This proton came from this particular star because it must have bent quite a bit. So in this sense, they have the same advantage as a photon or light, because light actually points back to the source. That's why we see all the stars very distinctly. However, neutrinos have one advantage over light, which is that they do not undergo much obstruction in the sky. So light, for example, can come only from the surface of the sun. It can come only from surface of stars. So if you want to see something happening inside stars or inside active galactic nuclei, we are sure that light cannot reach us. However, neutrinos from such places can actually reach us, and therefore we can observe processes happening inside stars if we can see neutrinos. We can see things happening near the center of our galaxy, for example, some of which may be shrouded by dust, but some strong source of neutrinos there can actually be seen even if you cannot see the source in light. Second, so they, in that sense, they are better than light. And another nice thing is that just like light comes in all wavelengths, you can see light in radio waves, infrared, ultraviolet, X-rays, gamma rays, and so on. Neutrinos also come at a large range of energies. So you see, this is from micro electron volts all the way to exa-electron volts. So 10 power minus 6 electron volts to 10 power 18 electron volts. So what do you get here? At about maybe micro to milli electron volts, we get our Big Bang neutrinos, which come from the electrons with neutrino energy of 2 Kelvin temperature neutrinos. Here there is a kind of a gap, but once you come to a few tens of keVs, you start seeing neutrinos from the sun. Then you see neutrinos from supernova burst, reactor neutrinos. You can see neutrinos from old supernovae. There is a large range around MeV all the way to giga electron volts or tera electron volts. We get atmospheric neutrinos. At higher energies, we get neutrinos coming from active galactic nuclei, and then neutrinos which are not yet observed, but we expect them to happen, are those which are called as GZK neutrinos. Let's not go into them. Maybe at the question time I can answer. But they are covering almost 24 orders of magnitude, and therefore they can be used to see the universe in many ways. Take the example of the neutrinos with the least amount of energy, which were these Big Bang neutrinos. The energy is of the order of 0.1 milli electron volts. Okay, and we already saw that compared to CMB, CMB is something we already know, right? CMB had 400 photons, 3 Kelvin, and they tell us about the surface of last scattering of photons, which was about 400,000 years old. Okay. Now this is actually very far back, because currently the universe is about 14 billion years old. So this is actually quite tiny baby universe that we know about if you look at photons. However, once we are able to look at neutrinos that come from cosmic neutrino background, which as we saw about 300 per centimeter cube, temperature of 2 Kelvin, they will tell us about the universe when it was about 0.2 seconds old. that's going really, really close to the Big Bang, because neutrinos decouple from the rest of the plasma very, very early, because they interact very weakly, so they decouple very early. So the last surface of scattering for neutrinos was when the universe was about 0.2 seconds old. So much before nucleosynthesis. In fact, before nuclei were formed, when things were in a soup of quarks and leptons. So therefore, these neutrinos, it's very important to measure them, and in fact, there are lots of experiments which are being proposed. It's just that the current experimental accuracies are quite far away from what we need at this stage. The kind of experiment people are looking at are experiments that use what are called as torsion balances, which are very precise experiments, but we are about a factor of million away from accuracy needed in torsion balances. Another kind of experiment that people are trying are experiments that look at beta decays again, but these are sort of induced beta decays. Okay? So perhaps not the time to talk about that right now. If you're very curious and we have time after the talk is over, I can give you a few pointers. Okay. So this is about very, very low energy neutrinos, which were here, okay? These green ones. Okay? Then I'll try to just mention you something about the supernova neutrinos, just because that has been my area of my work for last more than 20 years. And also because initially I sort of advertised that you need neutrinos to explode a star. So I'll just tell you a small story about how a star explodes. This is a star called as type 2 supernova, which means this is a very heavy star. And this star has a structure that looks like this onion ring. So outside is hydrogen, inside is helium, and you keep on going as with higher and higher nuclei till you reach iron. And all of you perhaps know that it is very difficult to go beyond iron when you are doing fusion, because iron has a very strong binding energy, and therefore at some point of time the fusion process stops. Now when the fusion was going on, the radiation from the fusion, okay, or in fact the pressure of even electrons there, which had high energy, was balancing the gravity, which is always trying to make the star small. Okay, gravity tries to bring everything together, especially in a star which is about 10 times the solar mass. Gravity tries to make it very, very small. While you are undergoing fusion, you have enough energy that you can keep the gravity, you can balance the force of gravity. But once your fusion stops, there is nothing for you to stop gravity from taking over, and this gravity then squishes the star so much that this collapse takes the density of the core to almost nuclear density, in fact even more than nuclear density. Okay? So the star gets squished into density of 10 to the power 15 gram per cc or so. And then, of course, nuclei have a hard core potential at the center, so that you can't go infinitely closer. You get a shock wave. Okay? It's like taking a big football, try to press the football together, and of course it will try to bounce back. This bouncing is something that produces a shock wave, which would finally end up exploding the star. The problem here is, of course, that gravity does not sit quietly. All these outer layers of hydrogen, helium, oxygen are still trying to come down. Okay? And therefore, if you just let the shock wave go out, very soon this shock wave will be overwhelmed by the infalling matter, and the supernova will not explode. What happens at this stage is that when the energy becomes the density becomes so high, that density becomes impenetrable even for neutrinos. Okay, now neutrinos have some cross section, which the lead which was required to be a few light years, the same light year thick lead has now got condensed into micron size. Okay, because density has gone up by a factor of 10 to the power 15. Neutrinos are then trapped behind the shock wave, and they try to come out. And to do that, they push the shock wave, and by the current understanding, it is this neutrino push that is essential for forming, actually exploding the star by forming what is called as an instability in hydrodynamics. So in this process, if you remember, if you notice, the four forces of nature, gravity, strong nuclear force, weak nuclear force, and electromagnetism, they sort of act in tandem, one after the other. This, by the way, is the Crab Nebula, which you can see in the sky. It's a very bright object at night. This was a supernova which was observed in the year 1054. So we actually have seen such supernovae. So why supernovae and why so much? The one reason was, of course, that we therefore learned how these heavy elements produced inside this star actually got to Earth. The second thing is that this number of neutrinos that come from the supernova is very, very high and give us a lot of information about what would have happened inside the star. Notice this number. Notice that this is a really high number, 10 to the power 58. Supernovae are really, really massive sources of neutrinos. Within 10 seconds, they give about 10 to the power 58 neutrinos, of the order energy about 10 MeV or so. I won't go into how, but let me just tell you in terms of what we studied, looked at some time back. If we observe this, within those 10 seconds, we'll be able to identify the neutrino mass ordering, which happens to be still an unsolved problem even after many, many years. On the other hand, we also learn a lot about supernova astrophysics by looking at neutrinos. One main thing that will happen is that neutrinos will tell us that a supernova is going to explode tomorrow in that part of the sky. The reason being that neutrinos actually start coming to us before supernova explodes. Okay, as soon as the shock wave collapses, neutrinos start coming out. Supernova explodes when the shock wave reaches its outer surface or envelope and the envelope explodes. Okay, so therefore we can see the supernova almost one day before it can arrive, and in fact inform all the other telescopes that supernova will happen in a few hours in that part of the sky. There exists a network like that, which in fact also gives me, would give me SMS on my mobile if that happens sometime. It hasn't happened yet for many, many years. Okay, you can observe many details of astrophysics inside a supernova, but for the lack of time, I will not go inside this. Okay, but in particular, you can actually see how a shock wave is propagating. You cannot see that in light because no light cannot come out unless shock wave breaks open the star. Okay, but we want to see the star before it breaks open, and that is going to need you with supernova. Okay, you can also see active galactic nuclei, which also have very, very high energies. The biggest detector we have right now on the Earth, which can detect neutrinos, is a detector called an IceCube. It's a detector which has 1 trillion liters of ice. Okay, but fortunately, we did not have to make up so much ice because the detector is based at South Pole. So what you see out here is the South Pole station. This is about 1.5 kilometers below South Pole. And for scale, this is the Eiffel Tower, which is often shown. Okay, so this size of the detector is about 1 kilometer by 1 kilometer by 1 kilometer. Okay, and it's a natural ice, so that's just used. So what you do is you don't pour ice or water inside detector. Inside ice, you put in photomultiplier tubes. So these dots that you see are actually photomultiplier tubes. So what you do is you go on the top, you start pouring hot water, which melts the ice, and you slowly lower these strings very carefully inside the ice. Make sure that they're aligned like this, and then wait till the ice freezes so that the strings are formed with the ice. Okay. And what can happen then is these strings, this ice just acts like the water detector that I showed you earlier, but of course much, much bigger than that. The particle is traveling. All of these circles that you see are signals in photomultiplier tubes. You can see various kinds of events. you can see track kind of events, or what are called as cluster events which are neutral current events and some new tau events and so on. So this detector is at the South Pole. It's going to continue its operation for many decades to come. It is going to look for astrophysical neutrinos from, again, many sources. I will not go into details of this. And this detector, just a few years ago, actually has claimed that it has seen some neutrinos with energy of 10 to the power 15 electron volts, which means that very likely these neutrinos have come from some astrophysical sources like atomic galactic nuclei. However, we'll know about that only when we do more and more observations. Neutrinos with even much higher energies can also be seen at various cosmic ray experiments by, again, many techniques. This is just to give you a sort of visual picture, and I won't go into details of exactly how that is done. Okay, keywords are here. So if you look for keywords like OJ or ANITA or balloon or Earth skimming neutrinos, okay, then you will be able to find exactly what happens. If required, I can answer later. Okay. So what all this has done is it has given rise to a new field called as multi-masonry astronomy. Okay. So what this means is, earlier we could look at the sky in many wavelengths of photons, gamma ray, X-ray, visible, radio wave, infrared. Now we have two more additions to this. One is neutrinos. So what this plot shows is, it shows the directions from which various neutrinos came to IceCube. So we'll know where the neutrinos are coming from. The right-hand side plot tells you about the two gravitational waves observed in 2015. So once we have information from light, from neutrinos and gravitational waves, then we can find something about any astrophysical processes in much more detail than we could have otherwise. Okay, so in fact this happened a few years ago in 2017, 22nd of September. IceCube saw a neutrino. It informed other detectors saying that, oh, a neutrino has come from that direction. There were some experiments on satellites which detected gamma rays. There were some radio telescopes on the Earth. All of these very soon found that there was a blazar. Blazars are objects that go off at unknown times in the Earth, or sorry, in the sky. And a follow-up of this was done in the next few months, and detectors kept on observing gamma rays coming from, radio waves coming from that direction. Okay, so therefore neutrinos actually help as this kind of harbingers. They tell you that something is going to happen very soon. Okay? So that's in some sense what observation of the neutrinos will tell us in a very short. In India, you perhaps know that we are trying to build a big experiment called as India-based Neutrino Observatory, or INO, which will use a very big electromagnet. In fact, it is going to be a 50 kiloton electromagnet, and this will be the largest electromagnet ever built on Earth. It will be kept inside this mountain so that there is a 1 kilometer rock from all sides, so no extra undesirable muons can come in. And because we use a magnetized detector, we can distinguish neutrinos from antineutrinos, which no other detector right now, no other big detector can actually do. Okay? So it can determine the mass hierarchy of neutrinos, for example. It's a reasonably good candidate. It has many more aims, and I will not go into this. Again, this is for you to go and look at later. But just note that this will be a very large-scale international experiment running in India for the development of experimental physics manpower. India doesn't have such a large-scale particle physics experiment yet, and it will be useful not just for physics but for biology, material science, geology, and so on. Okay. So once it comes up, I think it's going to open lots of opportunities, perhaps also for some of you. And even if you're not in physics, for engineers who will be needed in building such a large-scale experiment. I perhaps have taken a lot of your time, so let me just come back on my final concluding slide. Neutrinos open a new window to the universe in many ways. It allows you to look at extremely small scales like a microscope, because the mechanism for generating masses and mixing, which is quite unknown, happens at a very, very tiny scale, the scale of particle physics. It allows you to look at very large scales like a telescope, because you can understand astrophysical or cosmological phenomena at very, very large scales. And the third thing, which I did not talk about in the talk, but again, this will provide you keywords to search for in future. It has a very major role to play in future nuclear non-proliferation, in looking at tomography of the Earth, how Earth density changes, in oil exploration, and in fact also in communication. So again, you can talk about it if there is time in questions, but otherwise these are things to sort of excite your mind and maybe try to go and look for what exactly neutrinos can do in these processes. Okay, so I will stop here and finally take questions if I have any.
Thank you very much. This was a different kind of talk, in fact, opening up many different directions which we are not knowing earlier. So thank you very much. So maybe we can take a couple of questions. First, the questions from the chat box.
Okay, so let me just check. Where will be? Okay. Can trajectories of neutrinos be affected due to extreme gravitational fields due to massive astrophysical bodies? So the answer here is in principle, yes. So the trajectory of neutrinos can be affected, yes. If so, how they correctly point back to the sources? It is similar to light, for example. We do observe gravitational lensing, but remember, we observe lensing in a very, very small cases, right? Most of the photons that come from the sky have come without being gravitationally lensed. Okay? That's the reason that when we look at a star in the sky, we know the star is there and not very far away. Okay? So a vast overwhelming majority of photons that come without gravitational lensing, because all said and done, there is a huge gap between stars and galaxies. Okay, the sky is made up mainly of empty space. But yes, in principle, if the neutrinos will pass close to extreme gravitational fields, they will break. Okay. Neutrinos come in a large number. Then how do we pinpoint its source outside of solar system? So again, one of the ways this can be done is because we can trace them backwards, right? We can see where they're coming from. Okay. If you are able to, for example, take the example of this blazar that I mentioned some time back. Ice Cube saw which direction the neutrinos came from. They tracked the neutrinos backwards and went back to some region of the sky. We of course know about the sky very well in photons, and we know that where this neutrino came from, in that region, there was a blazar which used to go off at some uneven intervals of a few years. Okay. But once we knew that it came from there, people observed that region of the sky, and within the next few weeks, as you said, that blazar was observed blazing in various frequencies. So yeah, so we can observe them because we can see where they come from. Okay. Of course, we don't see neutrinos, we see the charged lepton that they produce. But if you have very high energy, then of course the lepton travels in the same direction as neutrinos. How are we able to take time of production of neutrinos? Well, of course, no. Just like you take time of production of light, right? So if you look at light coming from, let's say, Alpha Centauri, we know that it came from Alpha Centauri, and Alpha Centauri is about again 4 light years away, and therefore it must have started. So we know the time of production by knowing about the source, how fast the source is. Neutrinos, because their mass is very small compared to their energy, travel almost with the speed of light. Yes, in fact, all the neutrinos that we have observed so far have been traveling with almost the speed of light. So once you know the source, you know when they were produced. Okay. One more question. What are the factors depending on which neutrino interacts, as all don't assure to interact? Okay. The interaction of neutrinos depends on what type it is, electron or muon or tau neutrino or antineutrino. It also depends on its energy. Beyond that, it is statistics. So the same kind of neutrinos, a trillion neutrinos at the same time can come, but most of them will pass and one of them will interact. And why this one interacts is a completely statistical process. Okay, it's a random process. And that's the way quantum mechanics works. Okay, quantum mechanics still will be able to tell you that 1 out of 5 trillion neutrinos will interact. But which one will interact is not what quantum mechanics can tell you. That's inherent uncertainty or randomness in quantum mechanics. You observe it in neutrinos all the time. Because all neutrinos are very, very same, but somehow by chance, 1 out of a few trillion interacts. And why that, we do not know. Yeah. Anything else?
Yeah, there is no question in the chat box, but if anybody
Sir,
directly. Yes, Satya.
sir, you said when the star collapses, due to the shock wave around that star, neutrinos are they're released out. Is there something else that happens due to the shock wave around the collapsing of a star, or only the neutrinos are released?
No, so let me tell you in short exactly what happens. Okay. So now you understood the process by which the collapse starts, right? The gravitational collapse starts. Okay. The density of the core becomes more than nuclear matter, and there's a bounce. Okay. So bounce gives you energy for the shock wave to go out. Now you have the shock wave going out and matter falling inside. Now these two things collide against each other, and then the question is who wins. Now, what's happening behind the shock wave? What is pushing the shock wave? All the other particles like quarks, leptons, electrons, protons, they interact quite a lot. Okay, so they bounce each other very soon. So the mean free paths are very, very small. Okay, however, neutrinos don't interact that fast. Okay, so their mean free paths are slightly larger, and therefore they can give the energy to shock wave more efficiently. And that's the reason the neutrinos push the shock wave and the shock wave goes out. Now, as the shock wave goes out, neutrinos can start coming out of the shock wave. Because now, see again, everything is probabilistic. So some neutrinos come out, some neutrinos cannot come out. Those which cannot come out get reflected. And remember, when something reflects, you apply a force. Even when a laser light bounces off a mirror, it applies a force on the mirror. So similarly, those neutrinos that can come out, come out. Those are those 10 to the 58 that we see. Those that cannot come out, they reflect off the shock wave like a mirror, and therefore apply a force on the shock wave. And the combined effect of all these neutrinos is to push the shock wave outwards. Okay? And if the shock wave is able to overcome this infalling matter, then shock wave wins and the star explodes. If the shock wave loses, then the star collapses back again. So the fate depends on how much energy neutrinos can give the shock.
Sir, you said the density becomes very high in that shock wave. So does it block photons?
Yes. So photons cannot come through the shock wave. See, photons can come out only when the shock wave will travel out. See, remember, photons are very simple to stop. No, I have my hand. I don't know if I can see my hand on the screen because I cannot see myself on the screen. Okay, a source of light can be stopped by simply my hand, right? It will not pass through my hand. So light is very easy to stop. So light cannot come out of shock wave. In fact, remember all the time when the shock wave is coming out, till the star actually explodes, a photon cannot come out. Because photon can be stopped simply even by a piece of paper. A piece of paper in your book can stop a photon from passing through. So photons are stopped, but neutrinos are not stopped.
So, sir, so that means we can't see all of this happening in process.
We cannot see this if you only observe photons. You can see this if you observe neutrinos. So that's the point I wanted to make. Neutrinos allow you to see processes which you cannot see in photons. So shockwave propagation inside a supernova cannot be seen in photons. If you only observe by optical telescopes, you cannot see the shockwave propagating. Okay? But if you look at neutrinos coming from the supernova, then you can see shock wave propagation.
Yes, sir. Thank you, sir.
Okay, so I see another question. From quantum mechanical calculations, the difference in mass squares is obtained on neuron. That is correct. How can we make order of estimation of mass of neutrinos? Okay, so there are also other ways how to measure mass of neutrinos, which I did not mention. Some of them actually come from cosmology. So if neutrinos were very heavy, the heavy particles become non-relativistic very soon. If the particles are very light, then they can exchange energies between galaxies. Now what this does is this affects the distribution of galaxies in our sky. Okay, this is again a very different topic, and perhaps we'll take another topic. Okay, so if you exchange energies very efficiently between galaxies, then the galaxy distribution will become more uniform. Okay, if you stop distribution of energies, then they will become clustered. So by looking at how uniform is the galaxy distribution, can tell you that neutrino masses cannot be heavier than about 1 electron volt. So that gives you sort of one upper bound on the neutrino masses. So we know that the heaviest neutrino mass is not more than 1 electron volt. And other limit, we of course know the lightest mass can be 0. We don't know how light a neutrino can be. So we know that the masses lie between 0 and 1 electron volt. So that is approximate range right now. Okay. If neutrinos are found to be their own antiparticles, will you have to change the structure of the standard model? The structure itself will not change. However, you will have introduced an extra ingredient to the standard model. So for example, standard model right now, in the form that it is, does not allow okay, so conservation of lepton number happens in standard model the way it is right now. Okay, at the scales that you see in normal interactions. Of course, I will not go into details. You do have a lepton number, but in a very different processes. But for example, you know that the sum of electron, muon, and tau neutrino is always conserved, at least as far as you can see the reactions. If neutrinos have their own antiparticles, then this would change. Okay? You would see, for example, that sometimes there is a nucleus which decays and gives you 2 electrons. Okay, 2 power negative electrons. Okay, and this is called as a process called as neutrinoless double beta decay. Now this process is impossible in the standard model. However, if neutrinos are their own antiparticles, you will see this reaction. Okay, so the structure, in the sense the fact that there are 6 quarks, 6 leptons, that will not change, but detailed properties, the rates of reactions, and some reactions will change, and some reactions will be seen which you would not have observed before. So predictions change. Yes.
Hello. So, hello.
Yeah.
Yes, go ahead.
Sir, in our laboratory, we use water and ice to observe the neutrino. Can we use any other material to observe the neutrino?
Yes. So actually, the rate of reaction of neutrino does not depend so much on the material. The reason water is used was, well, one is that because it's cheap. Because if you know that the rate of your reaction will not depend on material, then you will use the cheapest material possible. Okay? So water is good. Water is also used because the process by which you want to detect, remember in that particular experiment I mentioned, super Kamiokande, was Cherenkov light. Okay? So super Kamiokande Cherenkov light, this ice cube uses Cherenkov light. So you need something which is transparent to light. Okay? So the process that you're using is going to be measurement of light. Then water is good because water is transparent to light. That makes sense. However, there are detectors which use other technologies. So for example, the detector that I mentioned, this iono detector, will use iron. Now, why is iron used? Because that detector is made with the main aim of distinguishing between neutrino and antineutrino. Now, how can you distinguish them? You can distinguish them if you produce charged particles which bend in magnetic field. Okay. Now, if you want to bend in magnetic field, then water is not a good material, because water is not a magnetic material. Okay. So then you have to use iron. Okay, so the iono detector that is going to be built will actually use 50 kilotons of iron, because iron carries magnetic field very well, and you can see bending of light. So now, inside the iron detector, you will not see Cherenkov light. Okay, so therefore, the detection technique of iron detector will be different from detection technique uh, of water detector. Okay. There are other ways people use. For example, the detector that's being built right now in US called as Dune is a detector that is going to use liquid argon. Okay. So again, different detectors use different properties of materials which are tuned depending on what it is that you want to measure. So all detectors therefore are complementary to each other. Okay. The first detector that detected solar neutrinos actually used something which was used as a cleaning fluid. Okay, simply because it had chlorine, and the reaction that it was aiming for was interaction of solar neutrinos with chlorine to give you certain chemicals. So yeah, so it depends on what reaction you want to see in the detector.
Okay, sir. Thank you, sir.
So any comment on dark matter and neutrinos? How we can use neutrinos for dark matter first?
So strictly speaking, neutrinos are a part of dark matter. Okay. However, we know that they are very light, so they only form even less than the percent of dark matter that we expect. Okay, so that if it is not a major form of dark, if they had mass of more than electron volts, maybe they would have formed a major chunk. But now we know that they are much smaller than electron volts, so we know that they won't form much part of dark matter. So that's one. Second thing is, therefore, in dark matter detectors, okay, very often if you look at go to dark matter results and look at their plots, they keep on showing some constants, and at the bottom of the plot you will see what is called as a neutrino floor. And what it means is that when dark matter detectors become better and better, finally they will be able to detect neutrinos. Okay. So this is not whole of dark matters. Hopefully they'll detect something even before that. But uh, the final aim of the best dark matter detectors is to reach neutrino floor, which is to be able to detect neutrinos in the dark matter detector. That will actually assure us that they're actually seeing something.
So this ice cube kind of detectors, essentially they aim for counting neutrinos, right? So they do not look at the spatial distribution of neutrinos. Well, I was just worried
So they
about
can't.
the granularity of the detector setup in ice cube. So I guess they are not looking into the spatial distribution of neutrinos, right?
Yeah. So of course, yeah. So they the granularity is very very low because the photomultipliers are very far away. So firstly, what it means is they can only measure very high energy neutrinos, and these are very rare. So they only come one by one. Okay. It is only after collecting data for many years that they can look at spatial distribution. So, for example, in the plot here that you could have seen, so each of these crosses that you see is
Yeah.
a neutrino. So this is the data of only the first few years, so we don't see many crosses. But once you have many neutrinos, this would be like a map of neutrinos in the sky, map of neutrino sources. So you can look at the spatial distribution, but it needs time. As I told you, neutrinophoresis means that you have to be very patient. You cannot get your next.
Not like accelerator physicists like us.
No. They get 10 to the power 15 events in a nanosecond.
Right. So this distinction between solar neutrinos and atmospheric neutrinos. So only the energy is the distinction. We make a cut on the energy, or something else is there which I am missing
So
because I
energy
am
and so energy and direction, for example.
direct.
The solar can come only from sun, or maybe a few degrees around that.
Right.
Atmospheric can come all directions.
Yeah.
And the energy difference actually is quite a bit. The solar neutrinos are less than 10 MeV. Atmospheric are more than 100 MeV. So there's a
Right.
very big gap between them. So you can understand. But direction is very, very major thing.
Important. Yeah. Okay, so any other question directly from anyone? We have taken quite a bit of number of questions. So thank you, having really showing nice patience as a true neutrino physicist.
It's fun.
So many questions we have taken up. So any direct question, one or two maximum? If not, so let me thank Professor Amol Dighe for the nice, exciting talk on neutrino. Possibly it was the first talk of this kind for me as well. Going to the really depth of neutrino physics from many different directions. And on behalf of IIT Indore, especially Department of Physics, so I would like to thank you for giving your time for this wonderful talk. And sometime we look forward to have you in our campus.
Yeah,
So
it was a pleasure. Yeah.
thank you.
Really in person. Okay?
Yeah.
Okay, bye.
So I'll stop recording here and